Of course, vibrating strings aren't the only way to make sound. We also know that we have wind instruments. So that sound made from a tube. So imagine if we have a tube of length L, and we want to find out what frequencies are available in the tube. So it turns out if we have, so the first case we'll look at is one open end. So we have a closed end of the tube and an open end. So we see that in this case, the fundamental mode would look like this. It's actually going to behave like an open string, which means in this case lambda is going to be 4 times L. So the frequency is going to be the speed over 4L, and of course this speed is the speed of sound in air. We go to the next wave up. So we add a node. Okay, in this case, lambda is going to be equal to 4/3 L. So the frequency is going to be 3 times the speed over 4L. And of course, we don't need to go any further. As you can imagine, this behaves just like an open-ended string. So we say that the frequency for a pipe or a tube with one open end is going to be n times the speed of sound over 4L, for n is equal to 1, 3, 5, and all the other odd integers. But now, what if we have a pipe or a tube that has 2 open ends? Well, in this case, as we saw here, the open ends are going to be, we don't have a node, we have antinodes at the open ends. So that means that the first wave that's allowed is going to look like this. So we see that lambda is equal to 2L. So the fundamental frequency is the speed over 2L. Of course, for the next wave, we add a node. So we see the next frequency that's allowed is for lambda is equal to L. So F is 2 times the speed over 2L. And so as you might guess, the frequency for a pipe with 2 open ends is n times the speed over 2L, for n is 1, 2, 3, 4, and all the numbers. So in other words, so a pipe with one open end behaves like an open string, and a pipe with 2 open ends behaves like a fixed string.